Welcome everybody. We're going to be continuing in this video our lesson on trigonometry in the coordinate plane. You previously learned how to use trigonometry with the unit circle, and we're going to be continuing that. But today in particular, we're going to be extending that lesson so that we're including obtuse angles. In the last video, whether you realized it or not, we kept using only acute angles. Alright, now let me tell you the significance of now introducing obtuse angles with trig ratios. Before you learned about the unit circle right here, you were always using right triangles with trig ratios. And so here's a right triangle right here. And whenever you found, or using a trig ratio, a sine or cosine, you were always taking the sine or cosine or tangent of one of the two acute angles of a right triangle. Never the right angle, and never an obtuse angle because, well, in a right triangle, it's impossible to have an obtuse angle. So this is brand new territory for us when we're working with obtuse angles in trig ratios. Alright, but if you're using a unit circle, it is possible to do that. All you have to be able to do is make an obtuse angle in standard position. I'm going to draw one of those right now, and then I'll explain to you the basic concept of how we're going to work with it. Here you see an obtuse angle in standard position. Remember, this is the initial side of the angle, and then we're going this direction right here. Alright, so that would be our obtuse angle. And whenever we're trying to find trig ratios involving obtuse angles, it's going to end up working out the same way in a unit circle as it did with acute angles. Remember that the point where an angle in standard position intersects the unit circle can be formed into a right triangle simply by drawing a perpendicular directly from that point of intersection to the x-axis. Alright, so there's the right triangle that we would be working with here. Now, it happens with obtuse angles that the angle theta in standard position doesn't fit inside of the triangle whatsoever. But this angle right here that is inside the triangle has a very special relationship to this angle theta, doesn't it? Those two angles together form a straight angle, or in other words, they're supplementary, so this would be 180 minus theta. Okay, now, still, it's going to turn out that the x and y coordinates of that point of intersection are going to correspond to the sine and cosine of theta. The cosine of theta will tell you the x coordinate for that point, and the sine of theta will still tell you the y coordinate for that point. Alright, this vertical distance here is equal to the sine of theta still, and this horizontal distance there is still equal to the cosine of theta. So there's lots of similarities between what we did with obtuse angles and what we're going to do, what we did with acute angles and what we're going to do with obtuse angles. Now let's look at a couple of obtuse angles and learn a little bit something about them. I want to start off with talking about sines of obtuse angles. Okay? And I'm wanting this in particular to show that the sine of 135 degrees is equal to the sine of 45 degrees. Now, I kind of described to you in the previous picture how you find the sine or cosine of an obtuse angle, but I also want to show you that there's a relationship between the sines of obtuse angles and very specific acute angles as well. So we're going to show that a couple different things are equal to one another. Let me start off with showing you how you find the sine of 135. What I would need to do is draw an angle that's 135 degrees in standard position. Now, if you think about that, here's 0 degrees, here's 90 degrees, here's 180. 135 is exactly in the middle of 90 and 180, isn't it? So the terminal side of that 135 degree angle would be right there basically. Alright, and the way we would find out what the sine of 135 is this. We would look at where it intersects the unit circle, and we would drop a perpendicular to the x-axis. And then we use this right triangle here in order to be able to figure out what the sine of 135 is. Now, I've told you in the previous slide again that the sine of an angle represents its vertical distance from the x-axis. But watch how we're going to find that. Alright, here's the 135 degree angle. which doesn't fit inside the triangle again. But what would its supplementary angle right here be that is inside the triangle? Well, it is supplementary. If you do 180 minus 135, you're going to see that that's a 45-degree angle inside of the triangle. And so if I wanted to find out, also remember the hypotenuse is 1 because it is a unit circle. If I wanted to find out what the sine of 135 is, it turns out that I can use the sine of 45 degrees to figure out what the sine of 135 degrees is. All right, just for simplicity's sake, let's, instead of the sine of 135, let's call this y for a moment. And we could say that y is equal to the sine of 45 degrees, right? We don't have to put the over 1 because the hypotenuse is 1. We don't need to bother dividing by that. All right, so what I've shown you then basically is that the sine of 135 is equal to the sine of 45 degrees. Now let me illustrate that a little bit more. If I were to draw a 45-degree angle in standard position, I'll choose a different color. Let's do this in red, let's say. Here's what that would look like, halfway between 0 and 90, of course. And let's show where it intersects the unit circle. Do you see a relationship, a geometric relationship between these 2 points right here? I hope that you notice they're reflections of one another in the y-axis. All right, and the point that I really want to make with that is that if you were to connect them, they're going to have the same y-coordinate, aren't they? Because they're reflections in the y-axis. And remember that sines correspond to the y-coordinates. So the sine of 135 degrees has to equal the sine of 45 degrees because the y-coordinates of where they intersect the unit circle are the same. All right, that's kind of enough there to show that the sine of 135 equals the sine of 45 degrees. And we would do the same basic thing with to show the sine of 120 is equal to the sine of 60. You'd want to draw each of those angles. So sine of 120 is going to be a little closer to 90 than it is to 180. So let's say about right there. There's its point of intersection. And let's go ahead and draw the sine of 60 degrees as well. Well, a 60-degree angle in standard position anyway. And that would be around here, let's say. Notice again that those two are reflections of one another in the y-axis. So the sine of 120 degrees equals the sine of 60 degrees. Now if you look at the right triangle that I created there from the 120-degree angle, you can again see that if you make a ratio, remember sine of 120 represents the y-coordinate there. If you make a ratio out of the sine of 60 and the opposite leg and the hypotenuse, the sine of 60 would equal the sine of 120 over 1. This is 1. And so sine of 60 equals sine of 120. Now, here's kind of the larger point that I want to make. Every acute angle, such as 45 degrees and 60 degrees, has an obtuse angle, such as 135 and 120, that has the exact same sine value. And there's a relationship that you ought to notice between the angle measures of two angles that have the same sine value. And that relationship is that they're supplementary to one another, right? 135 plus 45 is 180. Those supplementary angles have the same sine value. 120 plus 60 is 180. Those supplementary angles have the same sine value. Follow? All right. Well, let's summarize that last thought. Talk about the sines of supplementary angles. This is basically a property that you need to know. And it turns out that for any angle theta, the sine of that angle theta is equal to the sine of the supplement of that angle theta. Now, how do I show that the sine of theta equals the sine of its supplement? Well, if you were trying to find the supplement of, say, 50 degrees, wouldn't you subtract that from 180? So if I'm trying to find the supplement of theta, I would subtract theta from 180 to find its supplement. The sine of theta equals the sine of 180 minus theta every time. All right. And just to finish that thought before we go into cosines then, if I told you to write down the obtuse angle whose sine is equal to the sine of the given acute angle, well, you know that the angle that would have the same sine value as 30 degrees would have to be supplementary to 30 degrees, and so that would be 150 degrees, right? The angle whose sine would be the same as the sine of 78 degrees would have to be the supplement of that, which would be 102 degrees. Good. Now let's take a look at cosines. There's a certain relationship between the cosines and supplementary angles that we'll talk about as well. You may have, well, no, you probably didn't. Let's go ahead and just look at how you find the cosine of 135 and the cosine of 150, for instance. Let me go ahead and draw a 135 degree angle again. And we'll use much of the same thought processes that we did for the sine of 135 degrees, for the sine of an obtuse angle. There's our angle theta right there. It's 135 degrees. And we're going to use its supplement to help us find the cosine of 135. Now, of course, the cosine of 135 would be the x-coordinate for this point. Correct? Now, the cosine would end up then being the cosine of 45, or 45 would equal the cosine of 135 over 1, wouldn't it? Except that here's something very important that you have to realize. The x-coordinates in the second quadrant where we're at always are negative, right? This point has to have a negative coordinate and a positive coordinate. So, even though we know the cosine of 45 is the square root of 2 over 2, we can't say that the cosine of 135 equals the square root of 2 over 2, although it will be equal to a variation of that. It's going to be equal to negative square root of 2 over 2, right? Because it's in the second quadrant, x-coordinate has to be negative. We're going to say the cosine of 135 is negative as well. And actually, the cosine of every obtuse angle is going to be negative. If we look at the cosine of 150, we're going to use the cosine of 30 degrees to help us out. All right, and you might remember that the cosine of 30 degrees is the square root of 3 over 2. All right, except that then we're in the second quadrant, so the cosine of 150 would have to be negative, so it's going to be negative square root of 3 over 2. All right, now I need to draw you another picture here. I'm telling you essentially that you're using the cosine of 30 degrees in order to find out what the cosine of 150 degrees is, and I want you to see the relationship again. They're still using reflections in the y-axis like we were previously. So let's say that's our 30-degree angle right there. You still see that these are reflections in the x-axis, in the y-axis. But when we're talking about reflecting a point in the y-axis, the x-coordinate for this point is not equal to the x-coordinate for this point. The x-coordinate for this one equals the opposite of the x-coordinate for this one, don't they? So whatever this one is a negative value, this one would be as a positive value, and so forth. All right, now let me kind of summarize what I'm trying to show you. I'm trying to teach you a relationship between the cosines of supplementary angles, and that's this, that for any angle theta, the cosine of that angle theta is not equal to the cosine of its supplement, but it's equal to the opposite of the cosine of its supplement. So it's the opposite of the cosine of 180 minus theta. So just for example, let's just pick a couple of supplementary angles, say 40 and 140. The cosine of 40 degrees would equal the opposite of the cosine of 140 degrees. The cosine of 64 degrees would equal the opposite of the cosine of 116 degrees. All right, you got the pattern? Now, it happens to be these that are negative, right? The cosine of an obtuse angle is always going to be negative because that's in the second quadrant. And then these are positive. Good. One last thing that I want to try to get into your head in this video is I want to make sure that you know the signs, as in positive or negative, for the cosine of an angle theta and the sine of an angle theta, depending on where the angle is drawn in standard position. Thus far, we've drawn angles in the first quadrant in standard position, and now today in this video, we've drawn angles in the second quadrant in standard position. But you can obviously draw them in the third quadrant and the fourth quadrant. So we will have angles larger than 180 degrees that we'll be finding trig ratios for. And everywhere in the unit circle, if you pick a random angle, say this one right here, the x and y coordinates for the point of intersection that angle makes with the unit circle are always going to equal the cosine of theta, comma, the sine of theta. All right? No matter where theta is. And so one of the things you ought to be able to know is exactly in which quadrants is cosine going to be positive and negative, and in which quadrants will the sine of the angle be positive and negative. All right, let me erase that from the screen to make the picture a little simpler. All right, so remember the quadrants go counterclockwise, just like the degrees do in the coordinate plane. Remember, it goes 0 to 90 to 180. Well, we go quadrant 1 to quadrant 2, quadrant 3. In quadrant 4. And if we're thinking about the x-coordinates in each of these quadrants, well, in these two quadrants, the first and the fourth quadrant, x-coordinates are positive, aren't they? Whereas in the second and the third quadrants, x-coordinates are negative. And then we're looking at the y-coordinates. Well, the y-coordinates are positive in quadrants 1 and 2, and they're negative in quadrants 3 or 4. So that would tell me, for instance, that in the third quadrant, the cosine of theta is less than 0, it's negative, and the sine of theta is less than 0. And in the fourth quadrant, for instance, since the x-coordinates are positive, that would mean the cosine of theta would be positive, greater than 0. But the y-coordinates are still negative there, so the sine of theta would be less than 0. Some things that you need to be able to think through. All right, guys, thanks for watching. Hopefully you understand how to find the sine and cosine of an obtuse angle. See you next time.